Hello again. This time we'll talk about the Hausdorff dimension of the product of two Cantor sets again. So last time we've seen an upper bound for the Hausdorff dimension, and this time we'll see the lower bound. So what we want to show is that the dimension of the Cartesian product of two Cantor sets is equal to the logarithm of 4 divided by the logarithm of 3. So we've shown that this is an upper bound, and next we show that it's a lower bound. So this log 4 over log 3. In order to do this, we'll use the mass distribution principle. You can read a little bit more about it in Falconer's book about fractal geometry. But let's get into it. So let's start with the definition of a mass distribution. So a measure mu is called a mass distribution on F. So F is just a set in Rn. So if, again, let's say Borel, so F should be Borel, and then if, so the support of our measure is contained in F, and we want that the measure of F is non-zero and it should be finite. Okay, that's a simple definition, and now let's state the mass distribution principle, and let's prove it later then. So what does it say? So let's take a mass distribution on F and distribution on F, and we suppose that for some S, so of course S should be let's say non-negative, there are numbers c bigger than 0 and delta bigger than 0, such that mu of u, so the mass of this subset u, is at most this constant times the diameter of u to the s for all u which have a diameter at most delta. And then the claim is that the Hausdorff measure of this set with parameter s is at least the mass on the set F divided by C. And S is at most the Hausdorff dimension. So now if we can show this for this condition for S equal to log 4 over log 3, we have our lower bound for the Hausdorff dimension. So let's prove it first, this mass distribution principle. So let's take a delta prime cover. So a delta prime cover of F, so where delta prime is less than delta. So that means just these sets UI have diameters at most delta and they cover F. Okay, and now we use subadditivity of the measure, so we get 0 is smaller than the measure because we have a mass distribution, and then we get that this is at most the measure of the union because this thing covers F, and then we use subadditivity, so we get this is at most the sum of the measures of the UI. And now we have one more inequality, so we use our assumption, which we have here. So we use that all these UIs have diameter less than delta, so we get that this is C sum I equals 1 to infinity diameter UI to the S. Okay, so now let's see what do we have. So here we have this sum of the diameters to the S, and this reminds us of the definition of the Hausdorff measure. So taking the infimum, we get that H is delta prime of F is bigger than mu of F divided by C, because this holds for all such delta prime covers. So it also holds if we take the infimum and then taking the limit. This inequality, of course, still holds, so we get that Hs of F is at most, is at least, of course, this mass of F divided by C. And so we've proven the first claim, so this one, and about the second claim, this is actually follows the immediately from the definition. So because let's follow from the definition of the Hausdorff dimension. So let me just sketch it. So we have here we have S on this axis, and here we have the Hausdorff measure. So Hs of F, and here we have infinity. Then we have maybe there might be one finite non-zero point, and afterwards we have 0. And so we know that here it's the Hausdorff measure with parameter S is non-zero, so it has to be on this thing or possibly here. And so this means that the Hausdorff dimension is at most this S we have here. So we take, so this shows that S is on this line or maybe here, and so we get the Hausdorff dimension is at most Hausdorff dimension should be at most. What did I get wrong here? So let me. Yeah, that S is at most the Hausdorff dimension. Right, sorry. I got confused, but no. So that's it. Okay, and now we've have the mass distribution principle, and now we can go on proving the lower bound using this mass distribution principle. Okay, for this we use another proposition from the book of Falconer about fractal geometry. So, namely, it says, so we'll just give a special case of this proposition. So what we do, we've seen in the video about the upper bound that we can construct it, the product of these two Cantor sets as the intersection of these, let's call these E0 prime. Then we have E1 prime, so these should all have lengths 1/3, 1/3, and so on. And then we have here E2 prime, so let me just give you the complete picture. And then we go on, and we have seen that this is equal to the intersection of these EK primes. Okay, and what we do now is for each K, we give mass 4 to the minus K for all 4 to the K squares. And we do this, so this square gets mass 1, and here it still has mass 1, but we distribute it on the 4 different squares, and now we distribute it further, and so on. And the proposition tells us, so this was proposition 1.7 in the book by Falconer, so that this, so what I mean with give mass 4 to the minus K, at first we give here we take the Lebesgue measure on this unit square, and then take the Lebesgue measure here, and so on, but scaled every time. And then the claim is that this can be extended to a mass distribution on the product of the two Cantor sets. So we'll take this for granted, and then with this we have our mass distribution, and we can use this to prove the lower bound. Okay, so now this gives us already the strategy for the proof. So we have a mass distribution, and now let's see. So let's say we have that, oops, I don't want to parenthesis here. So let's say this holds for the diameter of some set U. So basically, let me show you the mass distribution principle again. So it says that we have this inequality for all sets U with diameter at most delta, and we'll actually show that this holds irrespective of the diameter, but in order to do this, we'll have to look it sounds contradictory, but in order to do this, we have to look at the diameter. So let's see. So if we have this, then we know that U intersects at most one square. So the diameter would be, so for instance, say U is somewhere, some set here, and we know it's, so if the diameter is less than, let's say 1/3 now in our case, it can't go from here to here or here to here and so on. So we know it intersects at most one square. So as we have these masses always contained in the previous one, so we get that the mass of this U is at most 4 to the minus k, because this square has mass 4 to the minus k. Okay, and what we want to show is that this is at most c times the diameter of U to the s. Okay, and of course our s here should be log 4 over log 3. Okay, that's what we want to show. And now let's see. So let's take diameter of U to the log 4 over log 3. And now this is bigger than 3 to the minus k. Let's see, the diameter is bigger, or let's say bigger than or equal to minus k plus 1 to the log 4 over log 3, which is equal to 4 to the minus k plus 1. Okay, and now we take c to be 4, and then we get that the measure of U is at most 4 to the minus k. That's what we have. That's what we have here, and which is 4 times 4 to the minus k plus 1, which is at most c, where c is 4, so that's what we have, and then the diameter of U to the s, where s again is log 4 over log 3. So what we get here is that log 4 over log 3 is at most the Hausdorff dimension of f by the mass distribution principle. So mass distribution principle. Okay, and that's the lower bound. That's what we wanted to prove. And so we finally get that the Hausdorff dimension of the product of two Cantor sets is equal to log 4 over log 3. And let me again remind you that in general, the dimension of the product of two sets is not equal to the sum of the dimensions. So that's in general not true, but there are instances where it is true. Okay, so that's it for today. If you have any questions, let me know, and have a good day. Bye.